Hey everyone, in this video we are going to be working with some NBA data, and it'll be pretty fun to look at with the NBA season starting, getting underway now. So really fun to look at it kind of like from a different lens. So we'll get started and we'll load in our library. So library tidyverse, library mgcv, and then library NBA StatR. And so we have those three, and if you don't have them, simply install that package is the name of the package. Okay, so with NBA StatR, you need to basically double your Vroom connection size because it uses a Vroom package that pulls the data that we need. So to do that, you just do sys set environment in quotes, Vroom connection size equals, and the default is 131,072 units. Just double that. And then what I'm going to do is add in a couple sources. So Todd Schneider came out with BallR, and it's really good for plotting shots and whatnot. So we're going to add plot court and plot themes. Feel free to copy this from my GitHub, but the URL is right here. Raw GitHub user content, Todd W. Schneider, BallR, master, plot court.r, and court themes.r. So we'll run both of those. So now let's get the NBA teams. From the NBA StatR package, we'll say NBA StatR, NBA teams, and then dplyr filter is non-NBA team equals 0, and ID division is greater than 0. So that way we get all 30 NBA teams. And so it might give you, a deprecated type thing, but gives us all 30 NBA teams. So now, what we're going to do is basically create a shot heat map of each player and look at either A, points per shot, or B, expected field goal percentage. And we'll say added or, lost. But first we need the season shots. So we'll call this season shots list since we're going to put it into a list initially. We'll say 1 NRow NBA teams per map function X NBA StatR teams shots team IDs equals NBA teams $ID team X and then seasons equals 2023. So seasons works up, so if you want the 2022-2023 season, you do 2023. If you want the 2023-2024 season, you do 2024. But we'll do last year since this year has a limited amount of data. And now we rip through it. Takes about 3 minutes or so. Now we have all the season shots. Let's bind those rows together. So season shots list, bind rows. And we have a data frame of every shot ever from every player in the 2022-2023 season. So now let's add some stuff. So we're going to add, instead of saying true or false, we're going to do ones and zeros. So we'll say shot underscore attempt if else is shot attempted equals true, 1 otherwise 0. Same thing for shot made. If else is shot made equals true, 1 otherwise 0. And then for the shot locations, we're going to make some adjustments so that way we can get it plotted correctly on the court. So we're going to say as numeric, as character, location X divided by 10, and make sure we get the negative of it. Again, this is solely for plotting purposes, so it fits with the court plots. Location Y as numeric, as character, location Y divided by 10 plus hoop center Y. And that you get hoop center Y from the plot court function. If you really want to do it without hoop center Y, just add 5.25. Now we'll add in points per shot, so PPS, case when, type shot equals 2-point field goal, and shot made equals 1, then 2, and I'll just copy this down a couple times. At the end we'll do true and a real. So that way, if it doesn't fit any of the criteria, it is an A. So now we'll change this to type shot equals 3-point field goal, and the shot was made 3 points. If there was a 2-pointer and missed, 0 points. 3-pointer and missed, 0 points. And so now we can run this, and I'll give you a little glimpse, something along those lines. So now that we have shots, let's create the general locations for each shot and get the averages so that way we can get above or below. So we'll say season shot percentage. Season shots, group by zone basic, because when we go into our data frame, we can see our zone basic. So what we'll do is basically from that heat map, we'll be able to create like a basic zone to say, hey, this is where guys shoot well or they don't shoot well. And then we'll say summarize makes equals sum shot made attempts equals sum shot attempt, and then points per shot sum DPS. And then we'll add a little bit more, so ungroup now, and then add a mutate, so league expected field goal percentage equals round makes divided by attempts 3, and league points per shot. So the league average points per shot in each zone and attempts. So then we'll select those few columns, so zone basic, league expected field goal percentage, and league points per shot. So that way it allows us to see, hey, here's our points per shot and in what area. So above the break 3, the league expected to shoot 35.5% with 1.063 points per shot. Backcourt, 2.5%, so think, those half court or above shots. In the paint, that's not in the restricted area, 44%. The point per shot is 88.7. Left corner 3, 38.5%, so on and so forth. So you can see like the restricted area is the most that has the highest expected field goal percentage and also has the highest points per shot, because you make a lot. But is it useful? And really, that depends on the player. So the reason why I use MGCV, because it allows us to create generalized additive models. And what a generalized additive model does is it allows you to basically create a heat map of prediction, or in this case, points per shot, expected field goal percentage, added or subtracted. So let's first create that function. So we're going to create a generalized additive model fit. So XFGAA is just basically expected field goal percentage above average. Create a function, and it requires one argument, which is D, which is just short for data. And we'll say GAM as numeric XFG PCTAA. We don't have that yet, but be wary. We will add that in there. This is just for plotting purposes. And then what are we going to model it to? The shot locations, of course. So loc X and loc Y. And the ASH just stands for smoothing, so that way we have a smooth and level playing field. And then last but not least, data equals D, so the data frame that we input to it. Same thing for points per shot. So I'm just going to copy this. But now, instead of expected field goal percentage, it's going to be points per shot. Then lastly, we're going to basically have a prediction grid. So our function to get those, predicted points per shot, expected field goal percentage, create a grid with the coordinates. So simply just expand grid, location X equals sequence -24 to 24, and we'll say we'll have 100 grid points there. Location Y is the vertical shot location, so 0 to 32, and the length is also 100. So what this is doing is basically creating that prediction grid within the shot coordinates. So -24 to 24 goes from sideline to sideline. 0 to 32 goes from basically the shot right under the rim all the way to a little bit outside of 3-point range for spacing. So it allows us to then create that, and then we're basically creating like a probability. So then we'll say predict, fit, grid. Our type is just response. So we just want the response predictor for it. And again, this is the fit that we put in. So essentially we'll put in one of these two fits, because it is a fitted model, so it's just short for fit. And then be able to create our heat map. So let's draw our heat map chart. So let's run all of these to make sure they're in an environment. So you see, like, nothing really happens because we're just calling a function. We haven't really mentioned it at all or anything like that. So now let's create our shot heat map chart, which is our last and final thing. So within the shot heat map chart, we're going to create our function. Our player is one of the arguments. Our court theme is just simply court themes $dark. We want a dark court theme, and the type equals points per shot. So basically the shot heat map chart has 3 arguments. One is the player, any NBA player. The court theme, light or dark. I'm doing dark. You can change the light. And then the type, which is either points per shot or expected field goal percentage. So we'll say if type equals points per shot, we'll say P title, which is short for just player title, paste, player, points per shot above average heat map. And then our plot limbs which you'll see more about that in a bit, -1 to 1. And then our plot breaks is -1 to 0 to 1. So if it's a points per shot, you have those limits, because it's, again, above average. Otherwise, we'll do expected field goal percentage above average. Again, our limits are a little bit different, so 0.3 to 0.3, which again is just -30% to 30%. And our breaks also fit the same thing, but again, with a 0 in the middle. So now, we'll say DF season shots. So that season shots data frame that we created, we'll be referencing from that, dply our filter, name player equals player. And so what this is doing is just saying, from the argument player that you insert, filter the data frame of season shots from that particular player. So if you input Kevin Durant, Stephen Curry, Klay Thompson, so on and so forth, it will filter down to that specific player. And then we'll say that player shot percentage, basically doing the same thing that we were doing for the league, except for that specific player. So group by zone basic, summarize, makes equals sum, shot made, attempts equals sum, shot attempt, and then points per shot equals the sum of points per shot. Ungroup, and we'll mutate expected field goal percentage, again, same thing. But instead of the league, we are doing that individual player. So that player's individual expected field goal percentage and his expected points per shot. And then we'll just select zone basic, expected field goal percentage, and points per shot. So now we're going to, again, have another data frame where we're going to decide what we want based upon the argument of type that we select, so points per shot or expected field goal percentage. So, again, we'll do another one. If type equals points per shot, then df, the data frame that we created, we're going to actually remove points per shot. And then we're going to join the data. So when you join, when you already have piping operators and our data frame already set, so for this left join, that period references this data frame. And then shot percentage, and by zone basic. So again, we're joining that shot percentage data frame that we just created with the data frame of season shots, so that way we know that particular player's expected field goal percentage based upon each zone and their points per shot based upon each zone. And then we'll do another one with the league shot percentage, so season shot percentage by, again, zone basic. So that way we get both that individual player's data and the league, so that way we can compare the two. And here's how we're going to compare the two. Mutate points per shot above average. Like I said, I was going to mention it later, and here's where it's going to come in. PPS minus league points per shot, so that way we know the difference between the two. And then expected field goal percentage above average, XFG percentage minus the league expected field goal percentage. And then this is where we'll have the model, so the generalized additive model within this, and then we're going to predict with that data. And you'll see here in a bit shortly what I mean. So then else, we'll basically copy it and do the same thing. Except the only difference now is we'll do expected field goal percentage above average. And then last but not least, we obviously want to plot our data set. So using, again, from Todd Schneider's ball art, we'll plot court, geom tile, data equals the data frame that we created. We want to map our aesthetics, and our X and Y is our locations, and our fill is that basically that probability grid that we created. And then we'll add some really cool stuff. So we'll say scale, fill, we'll do veridicity. Feel free to use any of these that you want, and we'll add percentage with a bunch of spaces. You'll see in a bit shortly why we're undoing that once the plot's created, but basically it's to have the color scale kind of more spaced out, so that way we can see percentage plus spaced out. And then this is where the plot limits will come in. So limits equals plot limbs, breaks equals plot breaks. Our option, or our color option, is I like Inferno. Feel free to look it up and see what kind of color options you have with the scale, fill, veridicity. But I like Inferno, and that's what was used in the ball art example. And we'll say guide color bar, and we'll increase the bar width again just to fit with that percentage, and it's more spaced out. Add a plus sign, and we'll say geom path data equals court points, AES X equals X, Y equals Y. And again, this is from that source up here that allows us to plot the court that we want. And our group equals descending. Again, it's just for plotting purposes. And then our color equals court themes, or sorry, court theme lines. So that way we get our lines, and then we want to match our X and Y coordinate scale to our prediction scale. So our X limit will be -24 to 24, again, sideline to sideline. And then our Y limit is 0 to 32, which is right under the rim to, a little bit further out in 3-point range. And then chord fixed coordinates, so that way we don't get wonky scales. And then we want to have like a little bit of a legend, bigger legend. So we'll say legend text equals element text size equals REL, which is just basically saying allows basically like a release from it. And then GG title label equals P title, so that gives us the title that we basically dynamically create based upon player, and our subtitle is 2022-2023 season. So now we add this to our environment, shot heat map chart. Alright. Now that we have run that function, let's go back up and just double check that we have all the other functions run. So run this, and then grid predict. Not sure if I wrote it down earlier, but make sure you add grid at the end because we want that data frame. So then let's check out a shot heat map chart. So we'll do Stephen Curry, and our type equals points per shot. So this shows, if you zoom in, you'll see like the full title, but basically this shows that Curry is very valuable in the corners, but he's also valuable all across the court. Looks like he's above average in everything, but he almost gets a full 1 point per shot above average compared to the league in the corners, which is really cool to look at. And then expected field goal percentage, pretty much the same thing. A lot of value in the corners for Curry. Let's look at his teammate Clay. So we run this, and this is where we see a little bit of a difference. So inside the arc, and it looks like one side of the corner, Clay is below average. However, for most of the three-point area, he is above average in expected field goal percentage. Let's look at one more. Let's look at LeBron. So LeBron, is below average compared to the league across most of the area. It seems like in one corner he's roughly average to above. There's some areas where you can kind of see the color get a little bit more towards the pink side, which is right around average. But obviously most of his values getting to the rim as evidenced here. So we'll look at one more. So since the Nuggets won the title, Jokic. So anytime there's gray, it just basically indicates, hey, Jokic does not shoot there or does not have enough shots to get data points there. So it looks like his value, is right around the restricted area, middle area, mid-range. Some 3 points on the wings, but the corners are not a strong suit compared to league average. So it's cool to look at it this way, and maybe it could be a great idea to help players and teams optimize where they're shooting compared to the rest of the league. So thank you so much for watching. Really hope you enjoyed this video, and have a great day.